There are moments when, seen from above, Earth no longer appears as the calm and stable world we imagine. Out in the vast expanse of the ocean, enormous masses of clouds begin to coil into near-perfect spirals, as if an invisible force were sketching a living structure across the sky. The wind no longer moves randomly. It tightens, accelerates, and organizes itself into a unified motion, pulling in moisture, heat, and atmospheric energy. This is the moment a storm is born. It does not emerge suddenly or without cause, but rather as the result of a long, silent build-up of energy. In that sense, a storm does not feel like a mere weather event. It resembles a living system, something that grows, evolves, and sustains itself. The dense rotating clouds over the ocean resemble the fingerprint of the planet itself, as if Earth were revealing its own pulse. And in that moment, the storm is no longer just a physical phenomenon. It becomes something deeper, a manifestation of the planet's dynamic spirit. But that perception leads us to a more fundamental question. If storms appear so structured, so alive, then where do they truly come from? What transforms an ordinary disturbance in the atmosphere into a powerful system capable of reshaping entire regions? Why do only a few atmospheric fluctuations evolve into massive storms, while countless others dissipate without consequence? And more importantly, are these events simply random outcomes of natural variability, or are they expressions of a far more intricate planetary system at work? If you're interested in exploring questions like these, where science meets deeper perspectives about the planet we inhabit, consider subscribing and following the channel so you don't miss future content. Because the further we look, the more we begin to realize that what seems familiar often hides layers of complexity we rarely stop to examine. To understand storms, we first need to shift our perspective. Rather than viewing them as isolated events, we must see them as part of a larger, interconnected system. A storm does not exist independently. It emerges from the interaction between the ocean, the atmosphere, and the rotational dynamics of Earth. When sea surface temperatures rise above a critical threshold, typically around 26 degrees Celsius, a subtle but powerful process begins. Warm water evaporates, transferring heat energy into the air above. As this warm, moist air rises and encounters cooler layers of the atmosphere, condensation occurs, releasing latent heat. This release of energy causes the Alhawat to rise even more vigorously, intensifying the process. A low-pressure zone forms, drawing in surrounding air to fill the void. And as Earth rotates, the Coriolis effect causes these incoming air currents to deflect and begin rotating, giving birth to the characteristic spiral structure of a storm. What makes this system particularly remarkable is that it does not simply form and remain static, it evolves. Once a storm reaches a certain intensity, it begins to sustain and amplify itself. Moisture continues to rise, condensation continues to release heat, and each cycle strengthens the system further. This is a classic example of a positive feedback loop, where the output of the process feeds back into the system as an input, accelerating its growth. In this sense, a storm behaves less like a passive occurrence and more like an engine, a thermodynamic system converting heat from the ocean into kinetic energy, expressed through wind, rain, and pressure gradients. Yet the significance of storms extends beyond their formation and internal dynamics. At first glance, they appear purely destructive, and at the human scale, that is undeniably true. Storms can devastate cities, displace populations, and alter landscapes within hours. However, when viewed from a planetary perspective, their role becomes more nuanced. Storms act as mechanisms of thermal redistribution, transporting heat from equatorial regions toward higher latitudes. Without such processes, the temperature gradient between different parts of the planet would become far more extreme, potentially destabilizing the global climate system. In other words, storms are not merely agents of chaos, they are also components of balance. And it is precisely here that a deeper implication begins to emerge. If storms are part of Earth's natural balancing mechanisms, what happens when the conditions that drive them are altered? Human activity, deforestation, urban expansion, and the increase of greenhouse gas emissions is fundamentally changing the thermal and moisture dynamics of the planet. Warmer oceans mean more available energy. A more humid atmosphere means more fuel for storm development. Under these conditions, storms are not just likely to occur, they are likely to intensify, persist longer, and become less predictable. From this perspective, storms can no longer be understood solely as natural disasters. They begin to resemble signals, responses from a complex system adjusting to new inputs. And perhaps the most important question is not how powerful a storm can become, but what it is telling us about the state of the system we are a part of. Building on that broader perspective, the formation of a storm is not a random occurrence, but the result of a precise set of environmental conditions aligning at the right moment. It begins with the ocean, where the surface temperature must reach a critical threshold, typically at or above 26 degrees Celsius. This is not an arbitrary number. At this temperature, the ocean holds enough thermal energy to fuel large-scale atmospheric processes, but heat alone is not sufficient. The air above the ocean must also be rich in moisture, creating a reservoir of water vapor ready to be lifted into the atmosphere. At the same time, there must be a vertical temperature gradient, a difference between the warm surface air and the cooler air at higher altitudes. This contrast is essential because it creates instability, the very condition that allows air to rise rather than remain stagnant. Once these conditions are in place, the process begins almost invisibly. Warm ocean water continuously evaporates, transferring heat into the air just above the surface. This warm, moist air becomes less dense than its surroundings and begins to rise. As it ascends, it enters cooler regions of the atmosphere, and this is where a critical transformation occurs. The water vapor condenses into tiny droplets, forming clouds. But condensation is not just a visual change, it is an energetic one. As water vapor transitions into liquid, it releases latent heat, a hidden form of energy that had been stored within the vapor. This release of heat warms the surrounding air, causing it to rise even faster, reinforcing the upward motion. At the surface, this upward movement creates a void, a region of lower pressure. Nature, however, resists imbalance. Air from the surrounding environment rushes inward to fill this low-pressure zone. As more air converges at the surface and rises, the system begins to organize itself. The inflowing air accelerates, feeding more moisture and energy into the developing system. What was once a localized disturbance now starts to expand, drawing in energy from a wider area of the ocean. Yet, without one additional factor, this system would remain disorganized. That factor is the rotation of the Earth. As the planet spins, it introduces a force known as the Coriolis effect, which causes moving air to deflect rather than travel in a straight line. In the northern hemisphere, this deflection is to the right, in the southern hemisphere, to the left. As air rushes toward the low-pressure center, it begins to curve, and this curvature gives rise to rotation. Gradually, the system transitions from a chaotic inflow of air into a structured, rotating vortex. The storm takes on its characteristic spiral form, with bands of clouds wrapping around a central core. At this stage, the storm is no longer just a passive response to environmental conditions. It becomes a dynamic system shaped by the interaction of heat, moisture, and planetary motion. In essence, a storm can be understood as the product of three fundamental elements: thermal energy from the ocean, water vapor in the atmosphere, and the rotational dynamics of the Earth itself. Remove any one of these components, and the system cannot form. But when all are present and aligned, the result is a structure of immense power and complexity. However, formation is only the beginning. What transforms a developing storm into a powerful and potentially destructive system is its ability to grow, and more importantly, to sustain its own growth. This is where the internal mechanics of the storm begin to reveal a deeper level of organization. As warm, moist air continues to rise and condense, the release of latent heat does not simply dissipate. Instead, it feeds directly back into the system, intensifying the upward motion. Stronger updrafts draw in more air at the surface, which in turn brings in more moisture from the ocean. That moisture rises, condenses, and releases even more heat. This creates a self-reinforcing cycle, a positive feedback loop. Heat generates motion, motion draws in moisture, and moisture releases more heat. Each component amplifies the others, allowing the system to grow both in size and intensity. What is particularly striking about this process is that it does not require continuous external forcing once it reaches a certain threshold. As long as the storm remains over warm water and the environmental conditions remain favorable, it can sustain itself. In this sense, the storm behaves like a thermodynamic engine, converting the stored heat of the ocean into kinetic energy expressed through wind and precipitation. At higher levels of organization, the storm begins to exhibit characteristics that resemble a self-regulating system. The inflow of air at the surface, the rising columns of moist air, and the outflow at higher altitudes all become coordinated parts of a larger circulation pattern. Energy enters at the bottom, is transformed within the hammock, and is redistributed outward. The storm is no longer just reacting, it is operating. This is why storms can intensify so rapidly under the right conditions. A small increase in sea surface temperature can provide significantly more energy, which accelerates the feedback loop. Likewise, higher atmospheric moisture content increases the amount of latent heat released during condensation. Each of these factors acts as a multiplier, not just an addition, to the system's strength. And once the storm reaches a mature stage, it can maintain its structure for extended periods, drawing energy continuously from the ocean beneath it. What emerges from this understanding is a shift in perspective. A storm is not merely something that forms and dissipates. It is something that develops, adapts, and, in a sense, evolves. Its structure becomes more defined, its internal processes more efficient, and its impact more pronounced. It transitions from a fragile disturbance into a highly organized system capable of sustaining itself over vast distances. In conclusion, the development of a storm reveals a critical insight. These systems are not static or accidental. They are dynamic processes governed by feedback, energy transfer, and environmental interaction. A storm does not simply exist, it becomes. And once it does, it possesses the capacity to strengthen itself, to persist, and to reshape the environment through which it moves. As the storm continues to intensify and organize itself through these self-reinforcing processes, its internal structure becomes increasingly defined. What once began as a loose and chaotic disturbance now transforms into a highly ordered system with distinct regions, each playing a specific role in maintaining the storm's power. Understanding this internal architecture is essential because it reveals that a storm is not a uniform mass of wind and rain, but a complex system with layers of behavior and contrasting dynamics. At the very center of this system lies what is perhaps the most counterintuitive feature of all, the eye of the storm. This region is characterized by extremely low pressure, often the lowest within the entire system. One might expect such a core to be the most violent part of the storm, yet the opposite is true. The eye is relatively calm, with lighter winds and, in some cases, even clear skies. This apparent stillness is not a sign of weakness, but rather a consequence of the storm's organization. Air spirals inward at the surface, rises violently in the surrounding manatee, and then descends within the eye, creating a zone of relative stability. In a way, the eye functions as the storm's central equilibrium point, a kind of control center where opposing forces temporarily balance each other out. Surrounding this calm core is the most dangerous region of the storm, the eye wall. This is where the storm's Shakti is concentrated, where wind speeds can exceed 200 kilometers per hour and upward motion reaches its peak intensity. Here, the processes described earlier, moisture convergence, rapid ascent, condensation, and heat release, occur at their most extreme levels. The eye wall is composed of towering cumulonimbus clouds that can extend tens of kilometers into the atmosphere, forming a dense ring around the eye. It is within this region that the storm draws its strength, converting vast amounts of thermal energy into mechanical force. The contrast between the shant eye and the violent eye wall is one of the defining features of a mature storm, illustrating how stability and chaos can coexist within the same system. Beyond the eye wall, the storm extends outward into spiral rain bands, curving chute of clouds and precipitation that wrap around the center. These bands are not random, they are structured pathways through which air flows inward toward the storm. As this air converges and rises, it cools and condenses, producing heavy rainfall. These outer regions can span hundreds of kilometers, bringing intense winds and sustained precipitation far from the storm's core. The continuous cycle of inflow, uplift, condensation, and outflow ensures that the storm remains active across its entire structure, not just at its center. What emerges from this layered organization is a striking contrast. At the center, there is relative stillness. Just beyond it, overwhelming force, and further outward, a vast kshetra of persistent motion and rainfall. This juxtaposition gives the storm a paradoxical nature. It is both orderly and chaotic, stable and unstable, calm and violent. Such a duality challenges our intuitive understanding of natural systems. We often associate power with disorder, yet here we see that the most intense Shakti arises from a highly organized structure. In this sense, a storm embodies what might be called a natural paradox, a system in which opposing conditions coexist and depend on each other. This internal structure also reinforces the idea that a storm is not merely a destructive event, but a process governed by underlying principles. Each region, the eye wall, the rain bands, contributes to the system's overall function. The calm at the center is not separate from the chaos surrounding it. It is created by it. The hinsa of the eye wall is not random. It is the direct expression of energy being transferred and transformed. Every component is interconnected, forming a system that is both intricate and efficient. As we shift from the internal structure of storms to their distribution across the planet, another pattern begins to emerge, one that further emphasizes the role of environmental conditions. Storms do not form everywhere. They are largely confined to specific regions of the Earth, primarily within the tropics, where the necessary combination of heat, moisture, and atmospheric instability exists. These regions are typically located on either side of the equator, where ocean temperatures are consistently high. However, interestingly, storms rarely form directly at the equator itself. This is because the Coriolis effect, which is essential for generating rotation, is weakest at the equator and strengthens with latitude. Without sufficient rotational influence, the organized spin required for storm development cannot take hold. This geographical constraint highlights how delicate the balance of conditions must be. Even slight variations in temperature, humidity, or planetary motion can determine whether a storm forms or dissipates. It also explains why certain ocean basins are more active than others, and why storm activity tends to follow seasonal patterns, increasing when ocean temperatures peak. Despite these regional differences, storms around the world are often given different names depending on where they occur. In the Atlantic Ocean and the northeastern Pacific, they are called hurricanes. In the western Pacific, they are known as typhoons. In the Indian Ocean and the southern hemisphere, they are referred to as cyclones. At first glance, these distinctions might suggest fundamentally different phenomena, but in reality, they all describe the same type of system. The naming conventions are historical and geographical, not scientific. Beneath these different labels lies a unified structure and mechanism. Whether it is called a hurricane, a typhoon, or a cyclone, the system operates according to the same principles. Warm oceanal mire provide energy, moist air fuels convection, and planetary rotation organizes the flow into a Kumte vortex. The internal structure, the eye wall, the rain bands, remains consistent across regions. The processes of heat transfer, condensation, and feedback loops are identical. In essence, these storms are variations of the same phenomenon, shaped by local conditions but governed by universal laws. Recognizing this unity is important because it shifts our understanding from seeing storms as isolated regional events to viewing them as expressions of a global system. They are not separate occurrences, but interconnected manifestations of how the Earth redistributes energy. And as we continue to examine their structure and distribution, it becomes increasingly clear that storms are not anomalies within the natural world. They are integral to it, shaped by the same forces that govern the planet as a whole. As we move beyond the structure and distribution of storms, a deeper layer of understanding begins to emerge, one that reframes storms not as isolated katnai, but as functional components within the Earth's larger system. At a planetary scale, storms play a critical role in regulating energy. The Earth is not heated evenly. Regions near the equator receive far more solar radiation than areas closer to the poles, creating a persistent imbalance in temperature. Left unchecked, this imbalance would intensify over time, leading to increasingly unstable atmospheric conditions. Storms act as one of the mechanisms through which this imbalance is corrected. When a storm forms over warm tropical waters, it effectively taps into a concentrated reservoir of thermal energy. Through its circulation, it transports this energy away from the equator toward higher latitudes. Warm, moist air rises within the storm and is carried outward at higher altitudes, while cooler air is drawn inward at the surface. This continuous exchange redistributes heat across the planet, reducing the temperature gradient between different regions. In this sense, storms function as dynamic conduits, moving energy from where it is abundant to where it is needed. Without such processes, the contrast between hot and cold zones would become far more extreme, potentially destabilizing global weather patterns on a much larger scale. This role extends beyond temperature alone. Storms are also integral to maintaining atmospheric balance. The Earth's climate system depends on the continuous circulation of air, moisture, and energy. Storms contribute to this circulation by organizing large-scale Harkut patterns that connect the ocean and the atmosphere. They facilitate the vertical transport of energy, moving heat from the surface upward, and the horizontal redistribution of that energy across vast distances. In doing so, they help maintain a state of dynamic equilibrium. The atmosphere is never static, but through processes like storms, it remains within a range that supports stability over time. To better grasp this function, it can be useful to draw a biological analogy. In the human body, a fever is often perceived as a negative symptom, an indication that something is wrong. Yet, in many cases, a fever is part of the body's defense mechanism, an adaptive response designed to eliminate pathogens and restore balance. In a similar way, storms can be understood as the Earth's response to thermal imbalance. They are not inherently destructive in their purpose, rather, they are corrective processes. The intensity of a storm reflects the degree of imbalance it is attempting to resolve. From this perspective, what appears to us as chaos is, at another level, a form of regulation. This comparison is not merely metaphorical. Both systems, the human body and the Earth's climate, operate through feedback loops, thresholds, and adaptive responses. When certain limits are exceeded, corrective mechanisms are activated. In the case of the planet, storms are one of those mechanisms. They arise when conditions demand redistribution of energy, and they persist until that redistribution has occurred, or until the system no longer supports their existence. Seen in this light, storms are not anomalies within the system, they are expressions of it. From this perspective, we arrive at a crucial conclusion. Storms are part of the Earth's survival strategy. They are mechanisms through which the planet maintains balance in the face of constant energy input from the sun. Without them, the climate system would drift further from equilibrium, potentially leading to more extreme and less predictable conditions overall. In other words, storms are not just events that happen on Earth, they are processes that help sustain it. However, this understanding also raises a more pressing question. If storms are part of a delicate balancing system, what happens when the underlying conditions of that system are altered? This is where human influence becomes impossible to ignore. Over the past century, human activity has introduced significant taghirat into the Earth's climate system. Deforestation has reduced the planet's capacity to regulate carbon and moisture. Urbanization has transformed landscapes, altering heat distribution and surface properties. Most significantly, the emission of greenhouse gases has increased the amount of heat retained within the atmosphere. The consequences of these changes are already measurable. Ocean temperatures are rising, in some regions at accelerating rates. Warmer water provides more energy for storm formation and intensification. At the same time, a warmer atmosphere can hold more moisture, increasing the potential for heavy precipitation. These two factors, heat and moisture, are precisely the ingredients that fuel storms. As they become more abundant, the conditions for storm development become more favorable. This does not necessarily mean that the number of storms will increase dramatically in every region, but it does suggest that the storms that do form may become more powerful. Stronger tarp gradients, higher moisture content, and prolonged exposure to warmer miyah all contribute to systems that can intensify more rapidly and sustain themselves for longer periods. In addition, shifting climate patterns can alter storm tracks, making their behavior less predictable. Regions that were once less exposed may begin to experience more frequent impacts, while traditional patterns may no longer hold. The result is a shift not only in the intensity of storms, but in their overall character. They may carry more rainfall, produce stronger winds, and persist beyond historical norms. This makes them more difficult to forecast and more challenging to prepare for. In this context, storms begin to reflect not just natural variability, but the influence of human activity on the systems that govern them. Real-world examples illustrate this shift with increasing clarity. Typhoon Haiyan, which struck the Philippines in 2013, was one of the most powerful storms ever recorded at landfall, with devastating consequences. Hurricane Katrina, which impacted the United States in 2005, demonstrated how vulnerable even developed regions can be to extreme storm events. Cyclone Nargis, which hit Myanmar in 2008, resulted in catastrophic loss of life, highlighting the intersection of natural occur and human vulnerability. While no single storm can be attributed solely to climate change, the avroof that allowed such storms to reach extreme intensity are becoming more common. Taken together, these developments point toward a fundamental shift. Storms are still part of the Earth's natural balancing mechanisms, but the system they operate within is being altered. As the baseline conditions change, the behavior of storms changes with them. What we are witnessing may not be a breakdown of the system, but rather its adaptation to new inputs that are increasingly the result of human activity. This brings us back to the broader perspective introduced earlier. If storms are signals, expressions of how the Earth responds to imbalance, then their increasing intensity may be telling us something important, not simply about the storms themselves, but about the state of the system as a whole. As we extend this analysis beyond physics and climate dynamics, a more reflective perspective begins to take shape, one that situates storms not only within the mechanics of the Earth system, but within a broader philosophical context. When viewed from the scale of the universe, a storm is almost insignificant. It is a temporary disturbance confined to a thin layer of atmosphere on a relatively small planet orbiting an ordinary star. Against the backdrop of galaxies, black holes, and cosmic timescales, even the most powerful storm fades into near invisibility. It is fleeting, localized, and ultimately minor in the grand structure of the cosmos. And yet, this same phenomenon, when experienced at the human scale, becomes something entirely different. For those in its path, a storm is not abstract. It is immediate, overwhelming, and deeply consequential. It can dismantle infrastructure, reshape coastlines, and disrupt entire societies within hours. What appears trivial from a cosmic perspective becomes catastrophic from a human one. This contrast reveals an important truth. The significance of any natural event is not inherent, but relative to the system from which it is observed. A storm is small in the universe but immense within the context of human life. It is within this tension between scales that storms begin to take on a more symbolic meaning. Throughout this discussion, we have described storms in terms of energy transfer, feedback loops, and atmospheric balance. But there is another way to interpret them, not as conscious entities, but as expressions of how a complex system responds to change. When we say that the Earth reacts, or that it becomes restless or violent, we are not attributing human emotions to the planet in a literal sense. Rather, we are using language to describe patterns of response that resemble intention, even though they arise from physical processes. In this way, storms can be seen as part of the Earth's adaptive behavior. When energy accumulates beyond a certain threshold, the system reorganizes itself to restore balance. That reorganization may appear sudden, even aggressive, but it is not arbitrary. It is the outcome of underlying conditions reaching a critical point. The language of anger, or calm, becomes a metaphor for phases of imbalance and equilibrium, states through which the system continuously cycles. What makes this perspective particularly relevant today is the growing recognition that human activity is no longer external to these processes. For much of history, it was possible to think of nature as something separate, a background against which human civilization unfolded. But that distinction is no longer tenable. The scale of human influence has reached a point where it directly alters the parameters of the Earth system itself. When forests are removed, when oceans warm, when atmospheric composition changes, the system responds, not selectively, but according to its internal logic. This leads to a subtle but important realization. Nature does not speak in words, but it does respond in patterns. Storms, in this sense, can be understood as part of that response. They are not messages in a conscious or intentional form, but they are outcomes that reflect the state of the system. As conditions shift, so too do the behaviors that emerge from them. Increased intensity, altered trajectories, prolonged duration, these are not isolated anomalies, but indicators of a system adjusting to new inputs. The deeper implication is that humans are not observers of this system, but participants within it. Every action that alters energy balance, atmospheric composition, or ecological structure becomes part of the chain of causality that shapes future outcomes. This does not mean that any single storm can be traced directly to a single action, but it does mean that the cumulative effect of human behavior influences the conditions under which storms form and evolve. In other words, the boundary between natural and human-driven phenomena is increasingly blurred. From this perspective, storms challenge a long-standing assumption that humanity operates independently of the natural world. Instead, they reveal a more integrated reality in which human systems and natural systems are intertwined. The consequences of this integration are not always immediate, but they are inevitable. Every imbalance introduced into the system must, at some point, be addressed by the system itself. This brings us to the final reflection. If storms are part of the Earth's way of redistributing energy and restoring balance, and if human activity is altering the conditions under which these processes occur, then the increasing intensity of storms may not simply be a coincidence. It may be a reflection of the system's attempt to adapt, not in a conscious sense, but in a structural one, an adjustment driven by the same principles that have governed the planet for millions of years. In conclusion, storms are not merely destructive forces to be feared or avoided. They are integral components of a larger system, processes through which the Earth maintains its internal balance. To understand them solely as disasters is to overlook their function within that system. At the same time, recognizing their role does not diminish their impact. On the contrary, it highlights the importance of understanding how human actions influence the conditions that give rise to them. At present, there is clear evidence that the balance of the Earth system is being altered. Rising temperatures, shifting climate patterns, and increasing atmospheric energy all point toward a system under stress. If these trends continue, the processes that depend on those conditions, including storms, are likely to become more extreme. This is not a prediction based on speculation, but a logical extension of the mechanisms we have examined. The implication is straightforward, even if its consequences are not. If the conditions that fuel storms intensify, the storms themselves will reflect that change. And as they do, their impact on human systems will increase accordingly. This creates a feedback not only within the natural system, but between the natural and human systems, one that can amplify vulnerability if left unaddressed. The final image to consider is not one of chaos alone, but of response. The Earth does not act with intention, but it does not remain passive. It adjusts, redistributes, and rebalances. For a long time, these processes operated within a range that allowed human civilization to develop with relative stability. Now that range is shifting. The question then is not whether the Earth will respond, it already is. The question is whether we are capable of recognizing those responses for what they are and adjusting our own behavior accordingly. Because if we do not, the signals may become stronger, more frequent, and more difficult to ignore. At some point, what once seemed like a distant or abstract phenomenon may become immediate and unavoidable. And when that happens, the distinction between observation and experience disappears. The Earth will not need to whisper its state any longer. The response will be unmistakable, direct, powerful, and impossible to overlook.